All right, so what we're going to start today with is a lot of vocabulary because there's a lot of new vocabulary in this section to just even give us a basis to start off of. And we can't quite get to all of it today, so we will get to more of it tomorrow and make sure that we've kind of covered all of it by Friday. But giving us a place to start with, just our words, okay? Today we're going to talk about 3 different functions, and that is our position function. That is the one that we're used to seeing right now, and that is our base function. For us, that's usually been called like f of x or whatever. For whatever reason, a lot of times they will refer to a position function as s of t because most of our problems are going to be done in time. And that's fine. Don't be confused by that. It's whatever your base function is your position function. Typically, these are done in time, so our variable is a lot of times going to be t, and your position function will be the label of like feet or meters or some sort of position measurement. The derivative of that is your velocity function, okay, and that is the rate of change of our position function. So if I were to look at our position function's derivative, that will be our velocity function, v of t. That is typically abbreviated v of t. Just like we talk about doing the derivative of a function, remember that if this is in feet and time is done in seconds, our velocity then becomes feet per second. Because if we think about how we create a derivative, it would be our position function divided by time in our formal definition. And so this one would be in our units per time. For example, feet per second. Our third one is your acceleration function, and acceleration is the derivative of your velocity, so the second derivative of your position function. Typically noted as a of t. And it is the rate of change of your velocity function. So if we think again about doing the derivative of our velocity function, think back to your formal definition of a derivative. That would be the change of our velocity function over time. And if our velocity function, for example, let's say our position was done in feet, time was in seconds, so our velocity would be feet per second, that we would then have a fraction that was in the top, feet per second, over our t's, which are in second, and it becomes feet per second, or feet per second squared. Okay, so, and they will be written both ways, it doesn't matter, but it could be feet per second, or feet per second squared would be how we would see the labeling on an acceleration. And that's just a sample, it doesn't have to be feet, but just so you have an example to kind of look at and why. Speed is another question or another value that we're going to be finding today, and speed is velocity, but as always positive. So it's the absolute value of our velocity, or the absolute value of the derivative of our position. Displacement. Displacement is the difference between where our object starts and where our object stops during a given interval. It does not really take into account where it moves in between those times. It literally just cares where does it start and where does it stop. So if it talks about an interval from A to B, displacement is the position functions. It's the position, displacement is position functions. So I would do the position at B minus the position at A. Giving you kind of a visual, a lot of times we'll talk about like a particle moving along our x-axis, and if we had a particle that maybe started over here and at time A, and it moves over, let's say it moved over here, then back, and kind of went back and forth and then stopped right here. Displacement only talks about where it ends compared to where it started. and that would have been left 2 from where it started. It doesn't care that it like traveled all over the world to get there. Displacement is just beginning and end, to where it starts to where it ends. Okay? We're going to talk a lot about the movement of an object, and in a movement of object we would be asked when is it moving forward or when is it moving right, and those two are the same thing, forward and right, and those both happen when our velocity function is positive. The mathematical way, so we don't have to write out the words that velocity is positive, because we're going to have to justify a lot of this, is saying this: v of t is greater than 0 indicating positive. When is it moving backwards or left? That's when our velocity function is negative. So again, the mathematical notation for that is less than 0. Okay, so if velocity is positive or bigger than 0 and it's moving right, less than 0, it's moving left. So when would it be standing still? Well, it's standing still when velocity is exactly 0. So we would say our function is standing still, or our particle is standing still, when our velocity function equals 0. The thing that I would add to this is sometimes velocity is not the information we have, and we'll see some different situations where different information is given. So there are other things that can justify or tell us whether something is moving forwards or backwards, right or left. If all the information we had was our position function, for our velocity to be positive, our position function would be increasing. Now, increasing and positive are not the same thing. Increasing means going up as we move from left to right. Positive means above our x-axis. So make sure that you understand the difference between when something is called increasing versus being called positive. Those two are frequently confused with each other. Backwards would be then when our position function is decreasing. Okay, so if it's headed downhill, that would make our velocity function be negative, because it would be negative slopes. So that's just a second way. If all the information we had was by our position function, those are the things we would look for to say whether it was moving forwards or backwards, left or right. Okay, and then standing still would have to be at an extrema, at a max or a min. So a position function's maximum or a position function's minimum, that's where velocity is 0. Because that's where it would have a slope of 0. So position function, max or min. Other movement topics that we would talk about is when is something speeding up or slowing down. To talk about speeding up or slowing down, you have to consider 2 different functions, and that is your velocity compared to your acceleration. If your velocity and your acceleration have the same sign, they're essentially working together. Whether that same sign is positive or negative, it doesn't matter, but our particle would speed up, or our object would speed up, if the velocity and acceleration are the same. It will slow down if they are working against each other. One of them is positive and one of them is negative. We would say that our object is slowing down. Putting that into a chart side by side, velocity and acceleration, notice, it doesn't matter if they're both positive or both negative as long as they are the same sign. So when I look at the value at that given x value or t value, and they both come out to be a positive number, or they both come out to be a negative number, we would consider our object speeding up. If they have opposite signs, either way, our object would be slowing down at that point. Again, because then your velocity and your acceleration are working against each other. All right, other phrases that we are going to see. Asked to find our average velocity. Remember that average velocity is going to use actually our position function over time. So average velocity is that slope formula, right? If I were to change that to your average acceleration, we would use our velocity formula in there, right? Because again, we're using the function right above it. So if I were to change that to average acceleration, we would put velocity here over time. Down here it says instantaneous velocity, and I'm going to go ahead and put instantaneous in parentheses. It does not have to have the word instantaneous. If it asks us for our velocity, it's implying instantaneous velocity. Okay, and that is just your derivative of the position function at that time. All right, so finally taking all of those new words and vocab and such and putting them into some examples and how can we attack each of these. It says a dynamite blast shoots a rock up with a velocity of 160 feet per second. It reaches a height of h, and I would call that h of t, equals 160 t minus 16 t squared at t seconds, or t is measured in seconds. One thing I want to clarify in the top there, it says a dynamite blast shoots a rock up with a velocity. That's an initial velocity. They're saying at time equals 0. So when this rock shoots into the air, velocity of 0 equals 160. That's what this is saying. Velocity at time equals 0 equals 160. Okay. So the first part says draw a graph of this scenario, avoid using a graphing calculator. So how can we draw a graph of what's going on with those two things? Well, think through what we're looking at here. I'm going to start with the position function, actually. Our position function, h of t equals, and as I scan through that, it's not in standard form, but it's a parabola, isn't it? It's got a t squared in there. You guys agree with that? And the number in front of the t squared is a negative, which means it's an upside down parabola. And it's the position of our rock. So think about a rock shooting up into the air. It's at some point going to stop going up, and it's going to come back down because we live on Earth, right? And so it's going to come back down to the ground. And that's exactly what's happening is we've got this rock that's starting at time equals 0 right here, shooting up into the air, and then eventually it's going to come back down to the ground. And that would be our position function, an upside down parabola, right? This would be our h of t. I can also graph on the same thing v of t. Now, first of all, v of t I know at 0 is up at 160. I know one more thing about my v of t, and that is that it's going to equal 0. Remember, it's the slopes of this graph, right? It's going to equal 0 when that hits a maximum. Isn't that a horizontal tangent right there? So we would have v of t hitting 0 here, hitting 160 here, and if I were to connect those two, now does it make sense the way I draw it? First of all, I know it's going to be a linear equation. Second, think about what it's representing. These are the tangent lines along here, and if I were to look at the little tangent lines along here, that's a positive number, positive value, right? That's a positive slope, positive value, positive slope, positive value. When we get to this side, on the other side of where it hits 0, now I'm drawing negative slopes, negative values. So you can see the slopes of the position function match the values of our velocity function. Yes? With all that? Okay. There's our picture of what's going on. What is the maximum height of the rock? Now, we're not using your graphing calculator, because otherwise I'd say type in h of t and use your max function, right? That would be really easy to do. But this is not a sample of a calculator question. This is something we can totally do without a calculator. I need to know what that is, right? I need to know that maximum height. Well, it's happening when this is at 0, isn't it? That's why I knew that that's at 0, because this is the maximum. So how am I supposed to figure out when that's happening? Our max height happens when our velocity equals 0, right? That's why our velocity equals 0, because it's a maximum there. And so that's what I can what I can use to figure out the time that this is happening. So right now I don't know what that is, but I can figure it out by setting my velocity equal to 0. Well, let's back up a second. I don't know what my velocity function is. I know what it is at 0, but I don't know what my velocity function is. So that's actually step number 1. We can figure it out, can't we? Velocity function is the derivative of our position function. And they told us the position function. So that's where I would start there, is I would find my my velocity function from the position function. So take the derivative of our position function, which is going to equal our velocity function. So now I'm just applying my power rule. 160t, the derivative of that is 160. 2 times 16 minus 32, subtract 1 from our exponent. That's my velocity function, 160 minus 32t. And I want to know where it equals 0. Where is it hitting my x-axis? So now I'm going to set that equal to 0. and solve for t. Okay. What is 160 divided by 32? 5. So it's happening at time equals 5 seconds, right? That's when it happens. That's not the question. The question is, what is the maximum height? Well, I right now know when it's happening. The height comes from the position, right? Position is going to tell me where it is. Where, what is the height of it? And we know the max is happening at time equals 5. So now I'm going to go to my position function and find where that rock is at 5 seconds by plugging in 5 seconds to our function. For time's sake today, you can probably just grab your calculator and figure out what 160 times 5 minus 16 times 25 is. What's the position of this rock at 5 seconds? 400. In this type of section with all of this, labels are going to be huge. Always label all of your answers. 400 feet. Question so far? All right. We're going to stick with that same scenario for a couple questions here. Next one, same setup here. What is the velocity and speed of the rock when it is 256 feet above the ground on the way up and then also on the way down? Okay. So if I know when that happens, I can just plug them into my velocity function, right? We know what our velocity, I've got my position function here. I know my velocity function from the last page. And if I knew when this happened on the way up, I could just plug it in and figure out what the velocity is. So that's where we got to start here, is when is it at 256 feet? I'm going to go back to this picture over here. We have a picture of what's going on. Remember that this happens up at 400 feet. So 256 is somewhere in here. And if I were to look at where that hits my position function, it hits 256 feet somewhere in there and somewhere in here. I'm right now trying to figure out what time that's happening so that I can plug it into my velocity function, right? That's kind of where we're at right now. Well, to do this, think about what you can do, and that is set your position function equal to that value. When does my position function equal 256 feet? So that's where we would start this. 256 is equal to my position function, and that will tell me what time that is happening. Well, I'm looking at a quadratic right now that I need to solve. So we've got options, and my options would be to either factor or quadratic formula, right? So in order to do that, I need to get everything on the same side equal to 0 first. Let's talk algebra for a second. I want my t squared function to be positive, so I'm going to move everything to the left-hand side here. I'm going to add 16t squared, subtract 160t, so that it's equal to 0. Also, if I remember my first step in factoring, this one becomes a lot easier because it has a GCF, doesn't it? All of those are divisible by 16. Okay, so then going through my factoring here, looking for factors of positive 16 that add up to negative 10, so they'd both be negative, multiply to give me 16. So anything that has a t equal to 0 and solve. And it looks like we've got two answers here. Time equals 8 seconds and time equals 2 seconds. Well, they ask us two different times here. We want to know what the velocity is on the way up, and we want to know what the velocity is on the way down. So go back and look at our picture here. We know that this happened at time equals 5, right? So at time equals 2, we're looking at on the way up. And at time equals 8, we're looking at on the way down. And I can see that easier on my picture here to know which one's up and which one's down. So going back to answer our question here, on the way up, I'm going to use time equals 2 seconds. They asked for our velocity, so I'm looking for velocity of 2. I'm just plugging that into my velocity function. Okay, let's see, 32 times 2 is 64. 160 minus 64 would be 96. We talked a little bit about our labeling on this one. If we're talking velocity, remember velocity is the derivative of our position function. We're talking in feet per second. Feet per second, so 96 feet per second. It also asks us to talk about the speed. And remember from several pages ago is that speed will equal the absolute value of our velocity. Well, our answer was already positive, so it's going to be the same, 96 feet per second. Speed does not account for which direction it's headed. It's just how fast it's going there. Okay? So then on our way down, we looked at the picture to decide that that was going to be at time equals 8. So we plug 8 into our function. It will hopefully make sense that these match, because if we go back and look at our picture, there's a lot of symmetry going on in this one, right? Those that are ahead of me on this, 160 minus 32 times 8, we get negative 96, right? Negative 96 feet per second. Speed, again, is going to be the absolute value of that, which would be still 96 feet per second. Questions? All right. Next one. This one, the most important part of this is the last part of the question. Still our same situation. It says, what is the acceleration of the rock at any moment of time? And they're going to ask you this about your velocity. They're going to ask you this about your acceleration. When it says that, all it's asking you to do is take your generic derivative. We're not plugging in any number. There's a good chance on a lot of those, especially velocity functions, that it's going to have a variable left in it. And they're just saying, leave the variable. Let it represent any moment of time, not a specific moment of time. Now, with that being said, go back to our velocity function. Okay, and we learned at the beginning that acceleration is going to be the derivative of our velocity function. So all I'm doing is finding my generic derivative, not at a specific time, but at t. Well, the derivative of our velocity function, that's going to be 0. That's going to be negative 32. It doesn't matter when it is. It's always going to be negative 32 because that's not ever going to change. But we wouldn't have left a variable there if it needed a variable. So let's talk about our label on this one. Again, remember, we're talking about the second derivative, and our acceleration is in feet per second, or in feet per second squared. Questions? When does the rock hit the ground? If we go back to when does the rock hit the ground, we are talking again position, right? We're going back to our position function, and I want to know when does it hit the ground. Oops, when does it hit the ground? Well, this is called when it hits our x-axis, a 0, and it comes from the fact that we set it equal to 0. So when does it hit the ground? That's when our position function equals 0. So go back up to our position function, set it equal to 0. Okay. Solve for t, because the question is when, so our answer is going to be time equals something seconds. Check out my GCF first. Anything that has a t gets set equal to 0. Continuing to solve, we find that time equals 0 or time equals 10. We have two answers, and we have to be able to figure out which one is when it hits the ground. Well, a time equals 0, isn't that when it's shooting up into the air? So then it comes back down and hits the ground at time equals 10 seconds. Questions? Okay. Continuing on, we're switching situations. A particle moves along a line so that its position at any time is greater than or equal to 0 is given by s of t equals t squared minus 4t plus 3. I'm going to stop there for just a second. This phrase right here, where time is greater than or equal to 0, hopefully that's going to make sense and be kind of implied. Can we have a negative time? I mean, time starts at 0, right? And a lot of times they'll continue to remind you of that. But if you were ever answering a time, you would not say that something happened at time equals negative 2 seconds, right? We will automatically throw out negative time answers because time always starts at 0 seconds. So they remind us of that right there, but that's kind of a common sense thing that we have to keep in mind as we are doing problems involving time. All right, so the first one says find the displacement of the particle during the first 2 seconds. Interpreting first 2 seconds means on the interval from 0 to 2. Time equals 0 to time equals 2. Displacement. Displacement is going to talk about your position. So we would look at our position, and we start with the end of it. Look at your position function at 2 minus your position function at the start at 0. And again, it's just the difference of where did we end, where did we start, how far did we move between those two spots. Well, if I look at my plugging those into my function up here, s of 2, let's see, 2 squared is 4, minus 8 would be negative 4, plus 3 would be negative 1. Check my mental math as we do these, okay. At time equals 0, let's see, I would plug in 0, 0 plus 3, so it would be 3. So our final answer, negative 1 minus 3, would be negative 4. Okay, now let's interpret that. I started at 3, I ended at negative 1. If I picture the x-axis, starting at 3, ending at negative 1, I moved left 4. So find the displacement. You can say negative 4, or you can say left 4. Next one, find the average velocity. Average velocity is going to use our position function in that slope formula, or average rate of change formula. During the first 4 seconds means on the interval from 0 to 4. I always think when they ask me an average one, go one function above what they're asking us for the average of. They're asking us for the average velocity. I use my position function in the numerator of that. So I would look for s of 4 minus s of 0 over 4 minus 0. That's slope formula using our position in the top. Okay, so let's see. S of 4, 16 minus 16 plus 3 is 3. 0, 0 plus 3 is 3. 0 over 4 is 0. So it looks like we would have 0 meters per second. Questions? Instantaneous velocity or velocity. Remember, to do instantaneous velocity, we just need to do the derivative of our function at 4. So we're going to look at the derivative of our function, which would give us the velocity function. Use our power rule, so this would be 2t minus 4, and we want to specifically know our answer at time equals 4. So our velocity would be 2t minus 4, evaluated at 4. 8 minus 4 is 4 meters per second. Okay, I don't think we're going to quite have enough time to do this last part justice because part E takes a little bit to talk through. So I will give you a little way to start that on your assignment, and then that's where we're going to pick up tomorrow. Acceleration, we just jump in from where our velocity, so our velocity function was 2t minus 4. Remember that acceleration is the derivative of that. So our acceleration would be the derivative of this, which would be 2. And again, if I evaluate that at time equals 4, it's still 2. Acceleration being meters per second squared or meters per second per second. Describing the motion of the particle involves talking about all of those functions. Where is it? So we start with our position. Position at time equals 0. Position when it changes directions, things like that. And talking about our velocity in there. Is it moving to the right or forward? Is it moving to the left or backwards, and on what intervals? And we'll start there. I'll give you kind of a preview so you kind of know what that question's asking you. You're going to see it in your assignment, and that's okay. We'll clean that up tomorrow. So like I said, tomorrow in our notes, we'll start there at part E and talk about how do we describe the motion of a particle given all of this information. All right. There is your assignment. We are going to spend a lot of class going through questions on that as well. I expect that we have questions on it, so make sure you come prepared, having tried all of those problems tomorrow, knowing that then you have an idea, you've thought through them, and I can clean up questions at that point.